All right, so this part will be a little bit tedious, and expect to pause it and check your steps along the way. So don't rush this, just if you want to see how the calculation follows. So I'll try to do it as simple as possible. This verification, again, the main idea is to give to the audience some motivation why we're going to need to use different computation rules that will bypass the need to replace Jn of x with its corresponding series whenever we need to manipulate it. So as I mentioned here already in the page, we need to verify that Jn of x given by this summation solves the Bessel equation of order n. So therefore, we must check that if I plug in Jn of x for y, and I expand that parenthesis, then I need to basically check that x squared jn double prime plus x jn prime plus x squared jn minus n squared jn is equal to 0. So what I'm going to do is I'm going to write a summation for all of these four components after I differentiate, of course, the jn of x. And again, at this point, assume all the convergence that we need. There is some theory behind it, to show that the series is convergent and all that kind of stuff. Assume that this is already proven. We're not going to deal with the theoretical part on proving this. Let's just basically verify the computation that indeed this is equal to 0, right, if I plug in that series. So let's differentiate first inside the summation. And we're gonna have to keep in mind the power rule and the chain rule when we differentiate this. So remember, everything is a constant besides x. Okay, so let's take first the first derivative, so jn prime of x. That's the summation from 0 to infinity, minus 1 to the k over k factorial n plus k factorial. And power rule now, n plus 2k x over 2 to the power n plus 2k minus 1, and then times 1/2 because of the chain rule. And look carefully here that this guy, this 2 to the negative 1, if I were to combine it with 1/2, that's going to be 1. So keep that in mind. I'm going to do it on the next step when I multiply jn prime by x. But keep this in mind that 1/2 in fact cancels with 2 to the negative 1 if I were to take it out of this parenthesis. Okay, so let's do the second derivative. And I think I'm going to do it on the same row here. So jn double prime of x is summation from 0 to infinity. Again, a constant minus 1 to the k factorial, n plus k factorial, n plus 2k. Now, again, another power rule, n plus 2k minus 1. I think I got greedy a little bit here. I don't know if I can fit it. And then x over 2 to the power n plus 2k minus 2. Yeah, I got a little greedy here. Times 1 over 2 to the power 2, because there's another 1/2 from the chain rule. So n plus 2k minus 2. Okay, so now when we plug in these guys in the summation, we have jn double prime multiplied by x squared. So let's start with that one. So we have x squared times jn double prime. I'm going to bring x squared inside the summation. So look carefully here, summation from 0 to infinity, minus 1 to the k factorial, n plus k factorial, and n plus 2k, n plus 2k minus 1. And notice now that x to the n plus 2k minus 2, if I multiply by x squared, this becomes n plus 2k again. And as I mentioned before, 2 to the negative 2 will cancel with 2 to the second. So when we simplify everything here, we're left again with x over 2 to the power n plus 2k. Okay, so x to the minus 2 will cancel with x squared. They become 1. 2 to the negative 2 with the 2 squared, again, they become 1. So that is the most compact form for x squared j n double prime. Moving on, let's do xjn prime, xjn prime. So jn prime over here is going to be multiplied by x. And so anticipate already that this x to the negative 1 will cancel with the extra x. 2 to the negative 1 will cancel with the 2 over here. So xjn prime will be minus 1 to the k factorial, n plus k factorial, n plus 2k, and then x over 2 to the power n plus 2k. All right, two more. We need to come up with, let's see, x squared times jn. So all the way go back to jn of x, we need to multiply this by x squared. Okay, so to account for the third term in the equation. So x squared jn carry over again, minus 1 to the k factorial, n plus k factorial. And now I'm going to have to remove the 2 out of these parentheses. So over is going to be over 2 to the power n plus 2k, because on the top, x to the n plus 2k, you need the extra 2 from x squared. Okay, so x squared times x to the n plus 2k now is x to the n plus 2k plus another 2. And finally, we need to write down minus n squared jn. Bring it again inside the summation. So we're going to have an extra minus with minus 1 to the k n squared, and everything else is the same. All right, so normally now if I sum this up, I should prove somehow that it's all equal to 0. Okay, I mean, if j needs to solve the Bessel equation, if I add them all up, then this should be equal to 0. The problem is I can't exactly combine all the summation in that form. So I want you to look very carefully that the powers of x do not align, so to speak, and the indexes, right? So I mean, the index starts from 0 in all of these cases. But the powers cannot be combined because they are shifted, so to speak. In all three equalities, except the third one, the first power of x is going to be n, right? So when I say the first, I mean when you replace k with the first index value, which is 0, you start with x to the n. K is equal to 0, x to the n. K is equal to 0, x to the n. But the third one, when k is equal to 0, the first power is n plus 2. So what I'm going to do is for these three equalities, first, second, and the fourth one, I'm going to write the first term outside the summation so that the power starts with n plus 2. When k is equal to 0, the power is n. When k is equal to 1, which is the second term, the power is n plus 2. And that will be in alignment with this. But now, because all three summations here will start from k equals 1, I'm going to have to make a shift on the third summation so that the first value of the index will be 1 as well. So I'm not going to change basically at all the third summation. I'm going to just make it so that it starts with k equals 1 to make it in agreement with all the other three summations. So when I do that, then I can combine the summations and then factor out the common terms and hopefully show that everything adds up to 0. Okay, so the first, second, and the fourth, we're going to write the first term outside the summation. So when k is equal to 0, we have minus 1 to the 0, which is 1 over 0 factorial n factorial and plus 0 factorial. So that's just 1 over n factorial. K is equal to 0 in the beginning. So I'm going to have n minus 1 and then x over 2 to the n. And then the same thing as before, but now starting from 1 to infinity. So I'm just going to copy everything else. Minus 1 to the k factorial, n plus k factorial, n plus 2k, n plus 2k minus 1, and then times x over 2, n plus 2k. All right, let's do this one again the same way. We're going to copy the first term, minus 1 to the 0. That's 1 again over n factorial. Then it's just n. And then x over 2 to the power n. And then the same summation, but now from 1 to infinity. Same thing, minus 1 to the k factorial, n plus k factorial, n plus 2k, and then x over 2 to the power n plus 2k. As I said before, the third one, we're going to make a shift in k, just to make it start from 1 as the previous ones. So here we're going to replace k with k minus 1. Okay, we're going to make the same summation, but if we start from 1 instead of 0, then everything here should be written again with k minus 1 instead of k. So minus 1 to the power k minus 1 over k minus 1 factorial n plus k minus 1 factorial. Let's look carefully here. If I replace k with k minus 1, this reverses back to n plus 2k. Okay, because we have n plus 2k minus 2 plus 2, right? So this is going to be x to the power n plus 2k. And this will be 2 to the n plus 2k minus 1, like that, in parentheses, or 2k minus 2. And finally, on the last one, again, we copy the first term, separated from the summation. Let's see. If k is 0, this is going to be a minus n squared on the outside, right? So minus n squared over n factorial, right? When k is equal to 0 over here, x over 2 to the power n. And then the rest, again, the same thing from 1 to infinity now. We can combine this. Actually, let's leave that minus out. So minus 1 to the k n squared over k factorial n plus k factorial x over 2 to the power n plus 2k. All right. We're going to do some couple of more sleight of hand, so to speak. Well, let's see how we can show that this really adds up to 0 in as simple way as possible, which is not simple at all. I know it's tedious, but if we look carefully, we perhaps can do this without moving on to another page. All right, so let's have this all in front of us in the same frame. Let's see what we have outside all the summations. So we have 3 terms, 1, 2, and 3, with some stuff outside the summation. So if you look carefully, here, here, and here, we have basically a common factor, 1 over n factorial x over 2 to the n. So when I add it up, if I pull out 1 over n factorial x over 2 to the n, we're left with what? Well, in the first part, we get n squared minus n. This is the remaining part. In the second term, we have just n, so I'm going to add it up here. There's nothing outside the summation in the third. term. In the last one, again, if I pull out x over 2 to the n over n factorial, I'm left with minus n squared. This cancels, so that's going to be 0. So 0 times 1 over n factorial, x over 2 to the n, which of course is 0, as it should. All right. Now comes a little bit of slightly more tedious part, and let's look very, very carefully what we're going to have here. When I combine these summations, this, and this, we can pull up some common factors. So let's identify what's the most efficient common factor we can pull out. So obviously, we can pull out x over 2 to the power n plus 2k. So inside the summation, pull out minus 1 to the k over k factorial n plus k factorial x over 2 to the n plus 2k. And let's write whatever is left in each summation. Okay, so in the first part, once again, I'm going to pull out minus 1 to the k factorial, n plus k factorial, x over 2 to the n plus 2k. I'm left with n plus 2k times n plus 2k minus 1. On the second term, I am left with n plus 2k. The third term is a little bit trickier. So pay attention here. If I pull minus 1 to the k, I'm left with a minus 1. If I pull n plus k factorial, that's like having an n plus k on the top. Now imagine, for example, you multiply both sides by n plus k. That'll make n plus k factorial on the bottom, and you're left with n plus k on the top. Over here. Same thing here. K minus 1 factorial. If you want to pull k factorial, imagine you multiply by another k, top and bottom. That will make k factorial on the bottom, so you're left with k on the top. So you have an extra k on the top. And there's another 2 to the negative 2 on the bottom, if you look carefully, because you pull x to the n plus 2k, you pull 2 to the n plus 2k, you're left with 1 over 2 to the negative 2, which is essentially 4 on the top. So all in all, from the third term, you're left with minus 1, 4k, n plus k. Finally, on the last term, you're left with just minus n squared, right? Minus 1 to the k factorial, n plus k factorial, this one part of the common factor, you are left with minus 1 n squared. All right, so let's expand all of these remaining terms. So let's expand this all the way through. N squared, 2nk minus n, 2nk plus 4k squared minus 2k plus n plus 2k minus, let's see, 4nk minus 4k squared, and then minus n squared. So if everything is done correctly, everything should cancel. So n squared with minus n squared, let's see, 2nk, that's 4nk goes away with this. 4k squared goes away with this. Minus 2k with 2k. Gosh, that's all satisfying, right? Everything goes away, n minus n, so everything is equal to 0. So whenever I actually teach this part of the lesson, sometimes people are really get very down in the classroom. And again, let me summarize and emphasize again what was the whole point of this. Because obviously, that's not how these functions are invented. It's not like someone basically dreams this format of Jn of x and then it just happens to be a solution. one determines these coefficients from imposing a solution in the form of a series. So there are some recurrence formula that lead to these coefficients. But I feel that in topics like this, it really feels really weird if I just state, here's the equation, and then trust my word that the solution looks like this really ugly power series. So at the very least, let's just do this exercise at least once to actually check that the solution is indeed the one mentioned in the book. So that's one motivation. And that's the reason why in the homework, I will ask you to do exactly the same process for the Bessel function of order 0. So the process will be much easier because when you replace n with 0, some of these coefficients are much, so you will see the whole process is much faster. But follow through with the same type of work, right? I mean, starting with j not of x, j0 of x. So you will have basically x over 2 to the power 2k. There's not going to be an n here. It's just n is 0. Compute these derivatives and then multiply them by x squared x, and so add them up and see if you get 0 to check that j naught of x is the solution of the Bessel equation of order 0. So the one without this n, right? It's going to be just this. And another reason is because, as I mentioned before, there should be a strong motivation for us to learn computation rules that bypass the need to write these series when we manipulate the Bessel functions. To give you an example, which we're going to deal with in the next lecture, for instance, one can show that, let me write it here. One of the properties which actually are given in that handout, I ask you to print it out from Blackboard. So here's one of the rules we're going to learn. So x to the negative n jn of x. If you want to differentiate this is equal to minus x to the negative n j sub n plus 1 of x. So you could basically come up with various rules like differentiation rules, integration rules, as you will see later, in which you give the answer in terms of another Bessel function. And that's a huge advantage, right? I mean, instead of replacing Jn with a series and then going through the whole tribulations with the summation, we have basically an answer in terms of other Bessel functions. So you have basically a list of computation rules involving derivatives or integrals or other recurrence relations that allows you to manipulate these functions without the need to write them down explicitly. That's basically the main motivation for this exercise of checking the solution. So this is enough for today. And we're going to continue next time with some other properties, like I said, of the Bessel functions. And hopefully in 2 or 3 lectures, we're going to end up with actually solving a boundary value problem involving Bessel functions. See you next time.